This deck introduces entity relationship diagrams, ERDs. Of course, to master the art of data modeling, you'll have to practice and you'll have to think. Creating a solid logical data design for an organization requires developing a detailed representation of the important relationships between people, places, things, and events. Relational models, like the ones used in SQL database systems, depict data as a schema consisting of a list of tables with rows, columns, and relationships. But even if you are designing for a NoSQL environment, data design begins with a specific list of entities and relationships. The ERD shown here depicts three kinds of things we want to track in a system: scouts, badges, and earned badges. The lines depict and quantify relationships between these entities. Do you see how these sentences include data from the previous diagram? They name scouts who earn badges. These logical elements can be organized in different ways in a system, but the place to start is realizing that there are two kinds of things we want to list: scouts and badges. Then we note that we are interested in the relationship between them. Scouts earn badges. ERDs, entity relationship diagrams, are supposed to help us organize a collection of data into a logical schema. To specify a schema, we do three main tasks. First, we list the entities to be represented. Next, we identify the attributes to be recorded for each entity, and then we assess and document the cardinality of important relationships between those entities. Identifying entities. Well, the word entity can be used different ways. A good place to start with defining entity is to use an intuitive definition that considers entities to be people, places, and things that need to be tracked. From a database perspective, events or even relationships might also be treated as entities in a logical design. Cardinality refers to the number of items in a group. For database designers, cardinality specifies how many items in one entity list can be related to each item in another list. That's a specific definition. How many items in one entity list, maybe 0, maybe 1, maybe many, can be related to each item in another list. Okay, we'll expand on that as the slides continue. Cardinality is usually assessed in both directions for a relationship. For example, a medical prescription is signed by one doctor, but each doctor signs many prescriptions. The cardinality of prescriptions to doctors is many to one. Many prescriptions to one doctor. Here's another example. Each person has only one driver's license in a state, and each license refers to only one person. This cardinality, people to licenses, is 1 to 1. One person, one license. One license, one person. 1 to 1. Let's go back to our Kids Club example. A scout in Kid Club can earn several badges, and each badge can be earned by many different scouts. So the cardinality of scouts to badges is many to many. Many scouts, many badges. Each scout can earn many badges. Each badge can be earned by many scouts. So, ERDs depict logical entities and the cardinalities of important relationships. Okay, this slide will need a little more explanation. We've already covered that ERDs depict logical entities and the cardinalities of important relationships. We don't document all relationships, just the ones we're interested in. Consider the one-to-many relationship between doctors and prescriptions as shown in the simple ERD here. Each doctor writes many prescriptions, but each prescription is written by only one doctor. The boxes on the diagram indicate that the doctor and prescription are entities. One box represents a kind of entity, doctors. The other depicts another kind of entity, which is an event, which is the event issuance of a prescription. The line in between them indicates that a relationship exists, while the word prescribes on the line names the relationship. The symbols at the end of the line depict the cardinality of the relationship, and you may recall that the cardinality here is 1 to many. The end of the line, as it goes from doctor to prescription, has a 0 and a crow's foot. We call those three lines branching out a crow's foot. The combination of a circle, standing for 0, and a crow's foot means that each doctor can have from 0 to many associated prescriptions. We can have a doctor who has not yet written any prescriptions, 0. That's why the line from prescriptions to doctor has a 0 on it. But we can also have a doctor who has signed many prescriptions. That's why the prescription end of the line also has a crow's foot. If we look at the line in the other direction, from prescription to doctor, each prescription has to have a doctor associated with it, and each prescription is understood to come from only one doctor. That's what the two vertical lines mean. Think of it as two ones. There's at least one, yet there's no more than one. This ERD documents the association between persons and driver's licenses. We know this is a license relationship because of the word on the line. You may recognize the symbol at the person end of the line shown here. One and only one driver's license is issued to a person. They can't have two, and you can't have a license without a person. Going the other direction, each person may have at most one license, but a person may not have any licenses. That is why the driver's license line end has a circle, meaning 0, and a single line, which stands for 1. The relationship between Scout and Badge is many to many. The line from Scout, where it touches Badge, has a 0 and a crow's foot. Do you remember what that means? The 0 means that there can be a Scout who does not have any badges, while the crow's foot means that each Scout can have multiple badges. And, as noted in the other line ending, there could be a badge, which no one has earned, perhaps a new badge, but each badge may have been earned by one or by many different Scouts. Our examples so far have not included a combination of a line, for one, and a crow's foot, for many. Can you figure out what that would mean? I'll give you a second. If we had that symbol on the right end of the line in this example, it would mean that each student had to have one badge, but they could have many. That is probably not true in this case because a new Scout would not have earned any badges yet. But in some other schema, this kind of symbol might well be correct. You may have noticed that each entity in the previous diagrams has an attribute marked with a PK symbol. In an ERD, this symbol denotes an entity's primary key. Being a primary key means two things. First, the primary key value uniquely identifies a particular item in the list. For example, the member ID, number 5 for example, is all you need to know to refer to the one and only Scout associated with that value. Secondly, the list for this entity is allowed to include any given primary key value only once. For example, there can be only one badge named hiking because badge name is the primary key, and only one Scout number 12 because member ID is the primary key. Hopefully you have the notation all figured out. Boxes for entities, lines for relationships, and line end symbols to indicate cardinality. If you don't feel confident interpreting symbols, you might want to go back and review before you go on. Data design is an iterative process. That is, a designer probably draws the picture one way, thinks about it a bit more, makes some changes, thinks, changes, thinks, changes, and so on until a good product is on the page. In the examples we have covered so far, we've actually seen some common problems. That is, things that should be improved before the schema is accepted. Entities that share one-to-one relationships often can be merged, and entities connected by many-to-many relationships often need to be supported by a bridge entity. Importantly, these are not hard and fast rules. Choosing between alternative designs can depend on a lot of factors. Here's a few. What reports do you expect to be able to generate? How is additional data generated? Where did it come from? Did it come from a different process or from a different department? What restrictions should apply? Are some items particularly sensitive? Well, as we will learn as you get more experienced in the data world, good data design is part analysis and partly art. In the case of persons and driver's licenses, as shown on the ERD above, we might be able to create a single person record and include the license number and issue date as attributes. Whether or not this is a good idea depends on the organization and its processes and goals. A motor vehicle division might combine the two entities because they only care about a person if they have a license, but an employer that required driving and recorded employees' driver's license numbers might keep them separate so they can more carefully protect the driver's license data or better manage data that comes in from an external source. Also, let's consider the primary key for this entity. In a state with millions of people, some will have the same name. Therefore, a name would not make a good primary key. A driver's license number would be better. There is a problem with many-to-many relationships. Data designs, both traditional relational databases as you would find in Oracle or SQL Server, and more hierarchical designs such as you might find in a document database, tend to have trouble with many-to-many relationships. The problem here is that you cannot record this kind of relationship simply by adding attributes to the involved entities. Stepping back, first we have to accept that having a single attribute with multiple values is not acceptable. This is not the time for a complete coverage of why this is a bad thing, but to illustrate why it's bad, consider this. How would you sort the list in order by earned badge in the example above? If you were sorting by earned badge, and if Sally, as shown in the table, has both archery and hiking badges, do you put this record in with the other rows for hiking or in with the other rows for archery? There's no right answer. Putting multiple values in a single attribute is not a good thing. In this case, if we were to add a member ID to the badge entity, we can only record one scout who has the badge. And if we add a badge name to scout, we can only record one badge for any given scout. This will not meet the needs of our system. Some database systems do allow multi-valued attributes that might store, for example, a list of badges a scout earned, like swimming, hiking, and archery, but this makes it much harder to manage integrity and performance. This example, by the way, demonstrates the need for database normalization. Bridging the many-to-many gap. You can resolve a many-to-many relationship in an ERD by using an additional entity. These special entities are called associative, composite, or bridge entities. The earned badges entity shown on the slide is a bridge entity. Its primary key consists of a combination of the member ID and the badge name. In a relational database, we would add a row in the earned badges table that listed, for example, 5 as member ID and hiking as the badge name. That would mean that the scout uniquely identified as member 5 has earned the hiking badge. You may recall that the line ends document the cardinality of a relationship. Each earned badge is associated with exactly one scout and with exactly one badge. Further, each scout and each badge can be associated with multiple items of the type earned badges. In a set of relational tables, the data might look something like this. Can you tell from the list how many badges Sabah and Sally have earned? 3 for Sabah, 2 for Sally. Can you tell which scouts earned the archery badge? just Sally, as listed here. The point of creating a model such as an ERD is to facilitate construction of a useful database. As you may have figured out by now, entities in ERDs are implemented as tables in a database. Attributes become columns in the tables. Primary keys and relationship lines can be implemented as database integrity rules. This deck was mostly about drawing ERDs, but creating entity relationship diagrams is all about working towards effective and efficiently manageable database schemas.